Okay, hello and welcome back. In this video, we will cover section 3.1, and this will be an introduction to linear equations in two variables. So far we've been looking at equations just in one variable, just some variable x, or maybe we called it some other letter. But now we'll be looking at equations that involve two variables and then ultimately how these can be represented in graphs. So first let's define what we mean by a linear equation in two variables. So let me just throw out a few examples. So something like 5x minus 2y equals 11. And we can call both x and y a variable here. So very similar to what we've seen before, but now we have two unknowns that are related to each other in some way. So looking at this definition, it says a linear equation in two variables can be written in the form ax plus by equals c, where a, b, and c are real numbers and where both a and b do not equal 0. One of them could equal 0, but not both at the same time. So what we have is an equation that's in this particular form. And technically, we could call that the standard form um, of a linear equation in two variables. But it could look different. So we could have something like y equals 3/4 x plus 1. This is another useful form, which we'll get to. We'll describe this in another video. But we could ultimately put it into this original form, this general form that they're describing in the definition. All we would need to do is move this term with x over to the other side, and then it would be in that more general form. So it doesn't have to look like this, but ultimately it can be made to look like it. We could have a very simple version, just y equals x. It's a linear equation in two variables. If we put it in this other form, if we move the x over, we could write it as negative x plus y equals 0 if we were to subtract the x over to the other side. And we could even say something like x equals negative 3. Now this looks like what we've worked with before, an equation in one variable, but we could say technically we have 1x plus 0y equals negative 3. So we can still view it as an equation in two variables where the number in front of the y in this case is 0, and it just deletes that, that variable. And these are called linear equations because we'll see ultimately we can represent them as lines to whenever we graph these. But first let's discuss getting points that would be on this line. So this section is on deciding whether an ordered pair is a solution to a given equation. So first let's define what they mean by an ordered pair. So we had two variables previously, x and y, and we can place them within parentheses with a comma between them. And this is how we represent a point in space, and we'll view this in a graph a little bit later. But first we want to decide if it's a solution to an equation. And by a solution it means if we plug in these particular values, this would be a value like what we see here, 1, negative 3. That means x is 1, y is negative 3. If we were to plug that into the equation, which is what we'll do in this example, and we get a statement that is true, then we would say that that ordered pair is a solution to the equation. Visually, this would mean that the point is on the line that's described by the equation. So I'll just say in general, if you're asked to decide if a ordered pair is a solution, so to decide if an ordered pair is a solution to an equation, you want to plug in the values of x and y. And determine if the resulting statement is true or false. So I'll show you what I mean by that. Let's look at this example. So we're given this equation, and I'll write it down a little bit bigger here. So we're given 5x minus 2y equals 11. It's a linear equation in two variables, x and y. And each of these points that they give us an x and y value. So let's look at the first one. We have 1 comma negative 3. This 1, the first entry is our x, and the negative 3 is our y. So if we want to determine if it's a solution to this equation, we'll just replace x with 1 and y with negative 3. So let's start again with the equation. 5x minus 2y equals 1. So instead of x, I'm going to plug in positive 1. Then instead of y, I'm going to plug in negative 3. And I usually write it using parentheses like this, and it can be helpful if we have to distribute any negatives or anything like that. So let's just evaluate the left side. Let's simplify everything and see if it's equal to 1. So we're kind of asking this question, is this equal to 1? So on the left side, 5 times 1 is 5. Negative 2 times negative 3 will be positive 6. Oh, and this is 11. I'm sorry. So this will make a little more sense. 5 plus 6 is in fact 11, which is true. So we can say the point 1 comma negative 3 is a solution to our equation. So this is a solution. Meaning if we plug in these values, 1 and negative 3, it makes the statement true. So let's see our second example. Let's look at part B. B gives us the point 3/5, comma 4. So 3/5 is our x, the 4 is our y. So I'll rewrite the equation again. We're looking at 5x minus 2y equals 11. So let's plug in 3/5 for x. So this will be 5 times 3/5. And 4 for y, so minus 2 times 4. Oh, and this is 11. Keep writing 1 for some reason. So is this equal to 11? So let's do the same thing. Let's simplify and evaluate. The first term, that 5, it's being multiplied by a fraction. If it's one of them's a whole number, I usually see it as a fraction 5 over 1. So that looks like it would be 15 over 5, or we could already cancel these 5s since I have 1 on the top and the bottom. So that should reduce to positive 3. And then negative 2 times 4 is negative 8. So is this equal to 11? 3 minus 8 will give us negative 5. If it was a plus, it would be true, but since we're subtracting, we'll get negative 5, which is not equal to 11. So we would say that this is not a solution. Or visually, we could say that this point is not on the graph of the line. But we'll look at plotting points and graphing lines. So again, if you're asked to determine if a point or if an ordered pair is a solution, just plug in the x and y values and simplify everything and see if you get something that makes sense. If you get a number equals itself, that means it's true. Or something like this, negative 5 equals 11, definitely not true, so the point would not be a solution. So let's look at a few more examples. This is the topic of completing an ordered pair, meaning we'll be given an x or a y value, and we want to find the value of the other variable that will make the statement true. So in this first example, they're giving us an unfinished ordered pair, negative 3 comma something. I can put a question mark there. So it's really asking us a question. When x equals negative 3, what is y equal to? So let's look at our equation. We have y equals 2x plus 10. So we have an x value to plug in, this negative 3. So let's plug that in and just see what y will be equal to. Here we already have the equation solved for y, so it'll be pretty straightforward. So I'm going to plug in negative 3 for x, so I'm going to replace it with negative 3. So I have 2 times negative 3 plus 10 equals y. So let's just simplify the right side. Now we just have a single variable. So 2 times negative 3 is negative 6. So negative 6 plus 10, you can view that as 10 minus 6. So that will give us positive 4. So it's saying when x equals negative 3, y equals positive 4. So that will give us the point negative 3 comma 4. So if you're given just one value, they might give you x or they might give you y. Just plug it in and then solve for the remaining unknown variable. So let's get some more practice with this. We can build a table of values, and that's what they're setting us up for here. So it says complete the table of values for each equation and write the information as ordered pairs. So let's look at this first equation. We have negative x plus 3y equals 8. And in the table, they give us one x value and then two y values. So let's just go one row at a time, plug in the value that we know, and find the one that we don't know. So for the first one, we can say when x equals 1, let's plug in 1 for x. So this would be negative 1 plus 3y equals 8. And then we just need to solve this for y. So that will become negative 1 plus 3y equals 8. Let's add the 1 over to the other side. So this will be 3y equals positive 9. And then divide both sides by 3. 9 divided by 3 will give us a positive 3. So on the table, when x equals 1, I can write a 3 for y. And we can view that as an ordered pair, or as a point, as we'll see in the next section, 1, 3. Okay, in the next row, they give us not an x value, but a y value. But the process will be the same. We can say when y equals negative 4, and then now, instead of plugging into x, I'll plug in negative 4 for y. So negative x plus 3 times negative 4 equals 8. And then we just want to solve for x. So I still have the negative x. 3 times negative 4 will be negative 12. And then I'll add the 12 over. So on the right side, it would be 8 plus 12. So let's say negative x equals 20. 12 plus 8 is 20. And then I can multiply or divide both sides by negative 1. Basically, the negative will move over to the other side. Let's say x equals negative 20. So I'll place that in our table. We have the point negative 20, negative 4. And then we get another y value. So we can say when y equals 2/3. So let's plug that in for y. We would have negative x plus 3 times 2/3 equals 8. So again, I'll view this as a 3 over 1. And then since I have 3 on the top and the bottom, those will just cancel. But we could also make it 6 over 3, which would reduce to 2. Either way, you would get to the same result. So this will become negative x plus 2 equals 8. Now we just need to solve for x. So I'll subtract the 2 over. So negative x equals 6. And then I'll need to move the negative over. So x equals negative 6. So that will go here. So now we have 3 points. And later on we will we'll see about plotting these points and then producing a line. So let's look at B. So notice the equation for B just says y equals 2. And they give us a bunch of x values to plug in. But in the equation, there's nowhere to plug in x. It's basically just saying y will always be equal to 2. If we wanted to, we could see this as 0x plus y equals 2, since there's no x's. And maybe it's easier to see here, anything that we plug into x will just be deleted by the 0. And we'll always get y equals 2 as the result. So on a table, I can just fill in 2 for all of these y values. It doesn't really matter what x is. Y will always be equal to 2. We'd see a similar thing if it said like x equals 2, then it doesn't matter what y is. We could plug in any value for y, and we get the same result. And we'll see this will represent a certain kind of line once we start looking at the graphs of these. But this was just some more practice of plugging in, being given one value, plugging that value in, and solving for the remaining variable. So let's start to see how we can plot these on a grid. So we're going to plot ordered pairs. So you may have done this before. We can build a coordinate system. If you have some graph paper, it's helpful to work with that, or you can draw your own graph. So usually start with two, what we call axes. I call this the x-axis, the horizontal axis, and the vertical axis is the y-axis. And each little notch on here will represent a value of x. And then each notch on the vertical axis represents a value for y. And the point at the middle, so this point at right where they intersect each other, call this the origin. It represents the point 0, 0. So remember when we see like a ordered pair, it gives us an x value and a y value. So we can see this as a sort of like directions to a location. On the x-axis to the right side, those will be positive numbers. So I can call this positive 1, positive 2, 3, 4. And then to the left of this central intersection, to the left of the origin, we get the negative x values. So negative 1, negative 2, negative 3, negative 4, and so on. On the y-axis, on top is positive, so I can call this positive 1, 2, 3, 4. And then beneath that will be our negative y values. So negative 1, negative 2, negative 3, negative 4. So a coordinate point, or an ordered pair, we can view as specific directions on where to go on the x-axis horizontally, and then where to go vertically in terms of the y-axis. So we'll get some practice plotting this. Overall, this is called the Cartesian coordinate system. It's attributed to Descartes, who is you may have read some philosophical works by him, maybe in a philosophy class, or you've probably heard of the phrase, I think therefore I am, and that's attributed to Descartes. But he also did a lot of work in mathematics, specifically in bridging algebra and geometry, and that's part of where this coordinate system comes into play. You can represent shapes, say like a circle or a line, in this two-dimensional space and attribute numbers to them and do some algebra. We can build equations. So it was a big step in the development of mathematics. So let's get some practice plotting some of these points. Let's look at our first example. So example 4 wants us to plot the point 4, 2. So again, the first term is our x value, and we can view that as a horizontal distance. So in the horizontal direction. And then our y value, we can view as a y distance, or a vertical distance. So let's build another set of axes. So again, this is the x-axis and then the y-axis. So each of these marks will represent one unit. And it's positive on the right side for x, so this is positive 1, 2, 3, 4. Negative on the left side. Positive above for y, so positive 1, 2, 3, 4. And then negative below. And notice this divides our area into 4 sections, and we call these the 4 quadrants. The one on the top right, call quadrant 1. That's where both x and y are positive. If I'm plotting a point in here, it's some positive x distance and some positive y distance. And then the quadrants are labeled counterclockwise. So the one on the top left is quadrant 2. That's where you have a negative x value and a positive y value. Then continuing counterclockwise, we get the third quadrant. That's where notice both x and y are negative. And in the bottom right, we call quadrant 4. That's where x is positive, but y is negative. So just to give some names for these locations. So let's plot our point and think about which quadrant we're in. We have a positive x distance of 4, and then a positive y distance of 2. So I would want to go out to 4. I want to count out 4 units in my x distance, and then from that point on the x-axis, we would go up 2 units. So over 4, up 2, and that's where our point will be. And we can label this 4, 2. So again, the first part of this is the distance on the x-axis. If it was negative 4, we would go in that direction. And then the second part of the ordered pair is your vertical y distance. So it gives us a location on this flat two-dimensional surface. And we're up here in quadrant 1. Both the x and the y's are positive. So let's get some more practice. Let's plot a bunch of more points here. Let's look at example 5. So let me build a bigger axis this time. Okay, and we put little arrows at the edge because this goes on infinitely in all of these directions. We could go as far as we want to. So let's practice plotting each of these points. Let's look at the first one. First one is -2, +5. So the x value is negative, and again, horizontal axis is x, vertical axis is y. So -2, +5, I would go over to the left 2 spaces, that's our -2, and then up 5, so 1, 2, 3, 4, 5, and that's where the point will live. -2, 5. So that was 8. For B, we have 1, -4. So now I would go to +1 in the horizontal distance and then down 4. So really I'm starting here on the axis and then going down 1, 2, 3, 4 and ending up there. So over 1, down 4, 4. We can label the point. For part C, we don't have a whole number, we have 5 halves. So that might be a little tricky, but we could count in halves. We have 5 of them, 5 halves. And there's 2 halves per unit. So we can imagine this would be 1 half, then 2 halves is 1, 3 halves, 4 halves is 2. So 5 halves would be in between 2 and 3. It's like 2.5. So 5 halves in the x distance, and then up to 3 units in the y distance. And that's where our point will be. We can call this 5/2, 3. So we can have points in between the unit markers here. We could have anything in between. And these don't necessarily need to represent like 1, 2, 3, 4. We could be counting in 2s or 5s or even thousands, depending on how we want to produce a graph. So it might be good to label these. If this is 1, 2, 3, this would be 6 out here. I think I went to -6 in that direction, down to -5 and up to +5 here. Okay, for part D, we have -5, -2. Both x and y are negative. It should land us in the third quadrant. So I'll go 5 spaces to the left, because it's -5, so 1, 2, 3, 4, 5. And then down 2, 1, 2, so somewhere over here. I'll plot my point. It's a little bit easier with graph paper, but we can still get the general idea of where these will be. So -5, -2. For E, 0, 1. So x is 0, meaning we won't move any distance on the x-axis. We'll just stay right in the middle, and then we would go up 1 space. So we would still be on the y-axis. Just at this point up here at +1. We can call this point 0, +1. And then for f, we have -4, 0. So this time we do have an x value, -4. So I'd go 4 to the left, 3, 4. This is -4 here. And then 0 for y, meaning we won't move up or down. We'll just stay on the x-axis. So our point will be over here at -4. -4, 0. So these are like little addresses. We can view an ordered pair as a location in two-dimensional space, or on an xy plane. It's another way of saying it. Or we could just say points on a graph. And later on when we're plotting lines, these kind of points will have special names, like -4, 0, 0, 1. The ones that remain on the axis, we'll call those intercepts. But more on that when we begin plotting lines. So let's look at another example. So it wants us to complete a table like we've done before, but now let's plot the points after we build out our table. So let me write out the equation. We have 2x minus y equals 5. And we have a couple of x values and a y value. So let's finish our table and then plot the points. The first one tells us that x is equal to 0. I can say when x equals 0, and then I want to plug in 0 for x. So this will be 2 times 0 minus y equals 5. 2 times 0 will just be 0, so that part will delete, and I'll get -y equals 5. And then I can multiply both sides by -1, or divide the -1 over, and it will appear on the right side. So y equals -5. So I'll have the point 0, -5. You can view that as a coordinate point. The next x value we have is 1. So I can say when x equals +1. So let's plug in 1 for x. This would be 2 times 1 minus y equals 5. 2 times 1 is 2. So 2 minus y equals 5. we can subtract the 2 over to the other side. So negative y will equal positive 3. And then, just like before, I'll divide the negative over. So y will equal negative 3. So I'll have the point 1 comma negative 3. And then for the third point, we're given a y value. So we can say when y equals positive 3. And then just plug in for y this time and solve for x. So 2x minus 3 equals 5. So that will just turn this into a minus 3. Then I'll add the 3 over, so 2x will equal positive 8. And then we can divide both sides by 2. So x will equal 8 divided by 2 is 4. So that tells us we would have the point 4 comma 3 on our graph. So let's plot these points. We'll just look at the right side, since all our x values are positive. So I'll add some marks here. So let's add our points. We have the point 0, negative 5. So 0 for our x, so we won't go anywhere horizontally, and we would go down 5 units. So we would end up at the bottom down here. Then our next point is 1, negative 3. So this time I would go over 1, and then from this down 3. 1, 2, 3. So I should end up here. And then our third point is the point 4, comma 3. So x is positive 4. So I'd go over 4, 1, 2, 3, 4. And then up 3 spaces, 1, 2, 3. So somewhere up here. Make that a little bit nicer. So the second point was 1, negative 3, and the third point was 4, comma 3. So these 3 points are solutions to our equation. And then notice visually they line up. If we were to draw a line through these 3 points, we wouldn't have to curve it at all. We'd get a straight line. Although mine's kind of curvy because of my sketchiness. But they do represent a line. So we can view in general any points or any ordered pairs that are a solution to this equation will appear somewhere on this line, somewhere on this slanted line. And this line goes forever. It goes forever in both directions. We could imagine little arrows here. So that tells us there's a unlimited number of XY pairs that will make this statement true. Pretty interesting to think about. But we'll get more into lines specifically in the next section. But just wanted to give a little hint of where we're heading towards. But that's why we're calling these things linear equations. Oops. Linear equations, because they represent lines in space. All right, let's look at an applied problem. So solving an applied problem involving ordered pairs. So this example says the length of somebody's hair is measured to be 250 millimeters, which is about 10 inches. And then they give us an equation for the length of this person's hair after a certain number of days, and we could represent it as an equation. And notice they say after x days, so x will represent the number of days of growth, where y is the actual length of this person's hair. And it's asking us a few questions. Using this equation, it wants us to find the length of their hair after 10 days, 60 days, and 90 days. And we could graph it. And then another question we can ask is, how long would it take, or how many days would pass for the hair to be a certain length? So let's look at the first one, for example. It's giving us a few values. So let me rewrite the equation. So y equals 0.30x plus 250. So notice this is like our starting value, 250. If we were to plug in 0 for x, and let's remember what x and y represent. X is the number of days that pass, and y is the length of hair. So let's just try to make sense of what this equation is saying. At the starting point, we have 250 millimeters, so we can say when x equals 0, meaning no days have passed, this term will get deleted, and we'll just say the length of the hair, which is y, is 250 millimeters, which is what the question told us. And then if we plug in 1 for x, we would add 0.3. If we plug in 2, that would mean 2 days go by, we would add 2 of these. So we can see this number in front of the x as like the rate of the hair growth. It's kind of telling us it's growing at 0.3 millimeters per day. So we'll equate that to the slope of a line eventually, but that will be in a later section. But just to get a sort of, try to start to build some intuition to what these equations can represent, as opposed to just being some problem that we're trying to solve. It actually describes some kind of behavior. In this case, it's describing the growth of this person's hair. So let's use the equation to find out how long their hair is after a certain number of days pass. So part A asks how long it will be after 10 days. So we can say, remember x is number of days, so they're asking us when x equals 10, what is y? So same kind of setup we've worked with before. So we can say, well, let's just plug in 10 for x. This would be y equals 0.30 times 10 plus 250. 0.3 times 10 should give us 3. It'll move that decimal place over. So this ends up being 3 plus 250, or 253. 253 millimeters. So it will grow those 3 millimeters in 10 days. And it wanted us to write this as an ordered pair. So our x value was 10, and the y value was 253. Okay, part 2. Now it asks after 60 days. So when x equals 60, so let's plug that in. We'd have y equals 0.30, this time times 60, plus 250. 0.3 times 60 should give you 18. So 18 plus 250. And then 250 plus 18 is 268. So 268 millimeters. So that's how long it'll be after 60 days, after about 2 months. So we can have the point with the ordered pair 60, 268. And then part 3 asks for 90 days. So that's our new x value. We can say when x equals 90, let's plug that in. So we'll have y equals 0.30, this time times 90, plus 250. So 0.3 times 90 will give you 27. So 27 plus 250, and then adding those together, you should get 277. So we can say after 90 days, the length will be 277 millimeters. So you see this continuous growth. So we can plot these points. It'd be a little bit tricky here because of the large numbers, so we'd have to do some scaling. Let's just look at part C. C asks, how long would it take for her hair to reach a length of 274 millimeters? So remember, y is the length of the hair, so this time they're giving us a y value and want us to solve for x, and that will tell us the number of days that will pass in order to produce that length of hair. So we can say when y equals 274, so let's replace that in our equation and then solve for x. So y is on the left side, 274 equals 0.30x, this time the x stays there, plus 250. Now let's just solve for x, and that will tell us how many days have passed. So I would subtract the 250 over 274 minus 250 is 24. So 24 equals 0.30x. And then we would want to divide both sides by 0.3. If you divide 24 by 0.3, it actually becomes larger. If you divide by something less than 1, it will grow in size. That should give you 80. Which makes sense, because at 90 days, we were at 277. So it should be sometime before 90 in order to get 274, a shorter length. Assuming there hasn't been a haircut in between. So x tells us this value, x equals 80, means it will take 80 days. For the hair to grow to 274 millimeters. So I think it's a good example just to show what these equations can represent. We can use them as a model of behavior. And once we have the equation, we can start to ask it questions and find out information that we didn't already know, just from a starting point. If we know what the equation is, we can find any length after any number of days, and from a reverse perspective, we can find out how many days will pass in order to grow to a certain length, and that's what we saw in part C. So you can imagine the same thing applying to many different situations. That's kind of the power of equations, building an equation that represents something in the world. You can start to make predictions and find out things that you wouldn't be able to normally. So that's part of the power of mathematics. All right, that concludes this section. So we were looking in general what a linear equation in two variables was. So something that can be viewed as ax plus by equals c, some equation that has two variables, x and y. And we decided whether an ordered pair is a solution or not by plugging in our x and y values. We were given one variable and asked to find the other one, so we completed some ordered pairs. And then we started plotting them on the coordinate system, and we finished by looking at that applied problem. All right, that's it for this video. Next time we will start graphing full lines themselves. So we'll see some techniques for graphing lines by plotting points and finding intercepts. All right, I'll see you next time.